Good day, my name is Chelsey Joane Lamam, and I'll be talking about my final year project, which is visualization of raw EEG signals using Python and deep learning. Paralyzed people and amputees need a device that allows them more mobility. Mechanical limbs and support like the Wilmer elbow provide very limited lower arm movement. Developing EEG BCI applications can provide maximum mobility for these individuals, but more research is required for accuracy enhancement of noisy EEG BCI signals. Deep learning has proved to be effective in EEG analysis, but better signal processing of EEG signals and deep learning model must be studied. Brain-controlled bioelectronic prosthetics are the future solution for amputees and paralysis individuals. Previously, the EEG signals are classified based on time series data. Hence, it is limited to utilize the advantage of CNN. A faster and more accurate method of translating raw EEG brain signals into robotic limb movements is required. This research utilizes a Python-based method to convert time-dependent raw EEG data into spatial matrix image form and utilize a deep CNN to classify the EEG spatial images fast and accurately. The aim of this research is to study the feasibility of spatial EEG datasets for BCI motor imagery using a deep convolutional neural network learning approach. The objectives of this research is to transform the time-dependent EEG datasets obtained into spatial data and feed it to the developed deep CNN for image classification. For the literature review, we focus on three main topics, which are non-invasive EEG BCI, EEG feature extraction and classification methods, and deep learning for MI EEG classification. BCI devices such as the Emotive Epoch headset has been used by Busetta et al. 2018 and Lieb et al. 2015 to study the feasibility of thought-controlled robotic arm movements to be used by severely motor impaired individuals such as amputees and paralysis patients. The optimizing of the frequency bands is prioritized to obtain meaningful feature attraction. An example of this method done by Feng et al. 2019 is the Common Spatial Pattern Rank channel selection for multi-frequency band EEG. For feature classification, EEG patterns of motor imageries are commonly classified using machine learning algorithms such as logistic regression done by Tang et al. 2015. Tang et al. 2017 established a CNN model consisting 5 different layers referencing spatiotemporal characteristics of MI-EEG classification task. As we observed, there are many researchers that studies the classification of EEG signals. However, not many researchers study the classification of spatial data form for EEG signals. Hence, this final year project puts emphasis on the significance of studying the classifications of EEG signals in spatial data form. For the research methodology, firstly we obtain raw EEG datasets, then we process the EEG signals before transforming the raw EEG data into spatial data. Then we optimize our deep CNN model before training the CNN classifier and validating the test data. For signal processing and filtering, we first acquire the data from BCI competition 4th dataset 2B. This EEG data consists of left-hand MI and right-hand MI from 9 different subjects with 5 recording sessions each. Then, we select only the first 2 sessions for all subjects because these sessions do not have the BCI feedback. Then, by utilizing the MNE module in Python, we bandpass filter all 6 channels for each recordings. All recordings are bandpass filtered with frequency of 8 Hz to 30 Hz. As for spatial data generation, we only select channels C3, C4, and CZ, which is the reference channel. All EOG channels are only for ensuring less artifacts in the EEG signals, hence why we do not use it to generate our spatial data. For the transformation of time-dependent signal to spatial data, epochs are created using events from annotations. Epochs are just a slice of time signal in this case. We have 60 epochs or MIQs for both left and right-hand MI. The EEG signal slices starts from MIQ and ends after an MI action is done. Using this process data, we can now generate a matrix image based on the epochs. The generated spatial data are shown on the left-hand side of the screen. For all selected channels, we get a matrix image that sums up all the MI recordings done. From this data, we select only the second up to the fourth second matrix image and combine all three images for all channels to form one complete EEG MI spatial data. This method is done for all the selection sessions for each subjects. In total, we have 18 spatial data for left-hand MI and 18 spatial data for right-hand MI. This is the general framework of our Deep CNN EEG image classifier. First, we input our spatial data to be fed into our CNN as training data. It undergoes 3 convolutions whereby feature extraction will be done before moving on to feature classification and outputting the results. The Deep CNN framework is built using Google Colaboratory. The results of this research shows that the model loss percentage of MI-EEG spatial image data classification for 20 epochs is able to be reduced. For test validation, the CNN image classifier is able to classify all test data with 100% accuracy, but this result may be due to less amount of training data. Therefore, further research must be done in order to increase the overall accuracy of the image classifier. This research found that the spatial image generated is not too feasible, as it is hard to determine the exact matrix size. Also, the underfitting or overfitting still occurs, causing some model loss. Besides, the number of spatial data for training is too small to achieve an optimal percentage of image classification accuracy. The spatial image can be further improved by using average spectral intensity for all epochs and convert the spatial image into a single-line matrix image. The model loss can be minimized by running trial and error to deduce the best fit epoch value. As for the number of training images, the training data for this specific EEG dataset can be increased up to about 1,300 training data if all the subject recording sessions are utilized. The use of Deep CNN for MI-EEG image classification greatly improves the accuracy and time consumption of the visualization process and classification of EEG brain signals, providing more development for brain-controlled robotic limbs. This novel association will have a significant impact in the medical field and will contribute to the development of robotic technological advancement, especially for real-life EEG BCI robotic machinery applications and system control. In conclusion, the feasibility of spatial EEG datasets for BCI-MI is studied by proposing a deep multilayer CNN for MI-EEG classification. The outcome of this research is that the deep CNN model proposed shows a higher yield of accuracy for MI-EEG image classification. The proposed classification method is significant for real-life BCI systems, including BCI-controlled robotic limbs for amputees and paralysis individuals. This research managed to transform the time-dependent EEG datasets obtained into spatial data using simple bandpass filtering and signal epochs. This research used a deep multilayer CNN to train and validate transformed spatial EEG data with high accuracy percentage and minimal loss. That is all for my presentation. Thank you.